Welcome back to Math 103. This is video number 2 on apportionment. A particularly important example of the apportionment problem comes from politics, and this is the example that we're going to keep coming back to in this chapter. The 14th Amendment to the U.S. Constitution says the following: representatives shall be apportioned among the several states according to their respective numbers, counting the whole number of persons in each state. Not 3/5 of a person, but the whole number of persons. So the 14th Amendment was ratified after the Civil War, after the abolition of slavery. Right? Everyone is counting as one whole person. The language here is noteworthy. Right? We have the language of apportionment and according to. So the idea is that the more populous a state, the more representatives in the U.S. House of Representatives it should receive. That's the general idea. But what about the details? What about the mathematical details of exactly how you decide from the number of people living in each state how many representatives it should receive in Congress? Well, no specific apportionment method is mentioned in the United States Constitution. The details are left to Congress to legislate, and over the course of American history, there have been several different apportionment methods, several different mathematical techniques for carrying out this process that Congress has in fact legislated. We are going to study those and how they work. To understand this more clearly, let's look at a map of congressional districts inside New Jersey. Right now, New Jersey has 12 congressional districts. That is to say that there are 12 members of the U.S. House of Representatives representing New Jersey, and one of them is elected by this district right here. Another member of Congress is elected by this district right here. Yet another member of Congress is elected by this district right here, which includes New Brunswick, where we are. All right. Now notice that these different districts all have different geographic areas, and God knows some of them have some very strange shapes. However, what they have in common is that each one has been drawn to have approximately the same population. Ideally, these districts would have exactly the same population, although it's hard to get that precise. Now, where did the number 12 come from? Why is the last district number 12? Ah, that is the output of a computation using a certain apportionment method, and we will understand how that method works. To establish the terminology we're going to be using throughout this subject, both in political and not political examples, here is the problem of apportionment in U.S. politics. We have to apportion seats. Okay, think of seats in the U.S. House of Representatives. Each seat represents one congressional district, right? So picture that there is a physical chair in the U.S. House of Representatives where your member of Congress physically sits when Congress meets. Okay? So we have to apportion seats, of which there are a certain number in total, currently 435. We have to apportion them among states. Think of the U.S. states. We're going to keep using this language of apportioning seats among states, even in non-political examples. How do we do this apportionment? Based on what? Well, based on population. In our political example, this is done every 10 years based on the results of the census. That means, roughly speaking, the more populous the state, the greater the number of seats it should receive in the apportionment. Ideally, if one state has double the population of another state, it should receive double the number of seats. In practice, it doesn't work out exactly that way, but that is the ideal. Now, recall, we said that New Jersey has 12 seats in Congress right now. That used to be 13. Okay, that number changes over time. It was only in the most recent census that New Jersey lost one of its seats. Now, here's a crucial point. Every state receives an integer number, a whole number of congressional districts. It is not allowed to have a district which is partly in New Jersey and partly in Pennsylvania. Okay, you cannot be a member of Congress who comes from New York and New Jersey. You have to be a Congress member from one state. Okay, so each district lies entirely in one state. Here's the problem then of apportionment. If we know how many seats there are in total, and if we know the population of each state, how should we compute the integer number of seats that each individual state receives? Typically, how many seats there are in total is given to you in advance. What the population of each state is given to you in advance. Right? So that's typical that all that information is known. Your job is to compute the number of seats going to each state. Right? So we're going to investigate 4 different mathematical approaches that have all been actually used in American history to solve this problem, including the one that's currently in use. To make sure that we really understand this, and to see how this applies outside of politics, let's try to understand what should play the role of population in a number of non-political examples. So before going on to the next video, look at these examples of apportionment problems and say what you think could reasonably play the role of population in each case. Right? So to help you, always talk it out like this. Buses are apportioned to bus routes based on fill in the blank. Nurses are apportioned to hospital shifts based on fill in the blank. Police officers are apportioned to neighborhoods based on fill in the blank. There's more than one way to fill in these blanks, but think about how you would do so.